All right, good evening, everyone. Let me just maybe make these slides available for download. I'm going to go back to chapter 8. There are some examples I want to take a look at as well. I believe we got to, I think we did the strain gauge as an example last time. So, yeah, so I think that's pretty much where we stopped. I actually wanted us to finish up with the resistive transducers last time, but we didn't have enough time. So I just want to quickly check. I think there's actually one more calculation that we need to do, which is, which is this for the thermistor. So yeah, but if we still have time left, I might go back to a previous chapter that we really haven't done lots of examples on yet. And anyways, just take a quick look here at some of our other resistive transducers, and then we can take a look at the thermistor. Okay, so the linear potentiometer. So essentially, there's a potentiometer which takes linear motion and basically translates into a changing resistance. So usually a linear potentiometer would look something like we'll usually take the form of a steel wire wound resistor with a sliding contact. So you're basically going to have two terminals and you're going to have a sliding contact. Now, you guys will see we're also going to make use of whetstone bridges extensively when we do measurements. The reason being is that a whetstone bridge gives you a nice stable reference, and on the other end you can have your changing value from where you are taking your measurements. And the nice thing about a whetstone bridge is you can use a differential amplifier to measure these voltages. And so you can measure those voltages and you don't have to worry about grounding. So believe me, if you want to build these circuits, grounding can become a bit of an issue. So a differential amplifier kind of isolates your output from any grounds, and that that can give you a bit more reliable results than using something like a just straightforward inverting or non-inverting amplifier, measuring directly from your transducer. Okay, but in any case, coming back to the linear potentiometer, so you can have so this RV2, this can be another linear potentiometer which generates your reference, or it can even be a rotating potentiometer, or just two resistors. So essentially, via your changing contacts, you basically have a whetstone bridge here. You just do this. So this RV2, that can easily then be something like a potentiometer to adjust the reference, and basically adjusting RV2 is basically your output is probably driving something that will control the pressure there. And so changing RV2 is then okay. Then basically what's going to happen is you're going to have a difference in voltage between these 2 points that can then be detected by your differential amplifier here. If there was no difference between those 2 voltages, there's nothing to amplify. Then the difference between them is 0. So this 0 amplified is going to give you 0. So yeah, but when there's a difference between those 2 points, then obviously that means that the pressure here is not what it's supposed to be. Your amplifier's output is then going to drive some process to either increase or decrease the pressure based on what has been adjusted here. And then, so then these bellows, this bellows capsule is then mechanically linked to that third terminal, or that middle terminal of RV1, and that will then adjust the voltage then accordingly up until there's no more difference between the 2 points anymore. Right, so that's something that can continuously happen based on the changes that you do on RV2 there. So RV2 is your reference potentiometer in this case. Then you get the rotating potentiometer. On the rotating potentiometer, yeah, so this is when you have angular motion or angular positioning that you want to translate into a resistance so that you can actually measure it, or into a volt, or to a proportional voltage rather. And yeah, so again, it's going to rely on the Whetstone bridge concept. But we also have the definition of resolution here. In fact, resolution is also applicable to linear potentiometers. So essentially what it is the voltage drop over 2 adjacent turns divided by the total voltage drop across the potentiometer. Or you can define the resolution as 1 divided by the number of turns of the potentiometer. Right, so a very straightforward calculation there. I'm not even going to do an example on that. It's very simple. There's not really any more complex that this thing can get. And then we have an example for a rotating potentiometer. So this looks a little bit more complex than our previous example, but I promise you it's not that much more complex. Okay, so the example that we have in the textbook is that of a cannon turret and its direction that the cannon is pointing. So you have your reference potentiometer and you have your feedback potentiometer here that is mechanically linked to a gear that's then on the running gear for the cannon turret there. So essentially, basically what happens here is if the voltage here on your reference or on your feedback potentiometer, if that voltage there, which is then on your comparator there, if those two voltages are the same, that means the cannon is pointing where you want it to point, right? So the comparator is going to output 0, so the motor is not going to do anything, and this cannon is just going to point in the direction that it is already pointing in. But let's say you want to rotate the cannon turret. This means that you're going to change your reference. So let's say we change it to that point on our potentiometer. And essentially what's then going to happen is you now have a difference in voltage at this point and at the at your feedback potentiometer, which comes in here on your comparator. So now you have a difference in voltage. Now that difference in voltage is then now that's now basically your error signal. That's then sent onto your motor control circuit, which then drives your motor. Your motor then drives a gearbox, which will then rotate the cannon turret. And while the cannon turret is rotating, so you have this little gear interface here between the cannon turret and your feedback potentiometer. So your cannon turret is essentially going to adjust your potentiometer up until the voltage difference is 0 again. Right. And then the cannon is then pointing again where you want it to point. Okay, so pretty simple. So the examples, they look very complex, but they really are not that complex. Okay, then we get to the circuit that I want us to do an example or two on. So we have the thermistor. So the thermistor is a temperature dependent component, so it will have its resistance change when exposed to change in temperature. Now the thermistor is a bit unique compared to what is the other one that we have? Not a thermocouple. It's also a resistive one. My goodness, I can't remember. Rheostat, yes, that's what I'm looking for. Okay, so rheostat, I think it's a rheostat. So, yeah, so the rheostat has a positive temperature coefficient. Thermistor has a negative temperature coefficient. meaning that its resistance will increase with a decrease in temperature, and its resistance will decrease with an increase in temperature. So typically what is done is, so in order to set up your whetstone bridge correctly, this voltage here, so let's say, under normal conditions or under room temperature conditions, if you will, the voltage here at this point needs to be the same as the voltage there at that point. Right, so then your bridge is balanced, right? And the easiest way to get the bridge balanced is just to have all these resistors equal in size to one another. Right, so then that's the easiest thing. You just get a bunch of resistors the same size as your thermistor at 25 degrees C, place them in, consider your bridge balanced. Now, what you're then going to do is you go place your thermistor where you want to measure the temperature, and you then connect it to your whetstone bridge, where your whetstone bridge would be in another room or whatever. Then, then you measure your temperature that way. So any temperature fluctuation that occur in the environment, then where your thermistor is placed, that will then cause changes in voltage V2 there, which we can then amplify via a difference amplifier or differential amplifier. Right, so we can go and calculate the resistance of our thermistor with this nifty little formula here. And this is for the resistance at different temperatures. The temperature, so RT there is the resistance at temperature T. So if it's at 30 degrees C, you can write it as R30, or however you want to do it. A is a constant. So mostly we will have to go and calculate these two constants from two different operating conditions given to us for our thermistor. But those constants, they're not too difficult to go and calculate. Then we can also have the temperature. So also take note that the temperature units here is Kelvin. So in order to convert from degrees C to Kelvin, so you'll definitely be given the temperature in degrees C. So to convert degrees C to Kelvin, so let's say for instance you have 30 degrees C. In Kelvin, that is just 30 degrees C plus 273. I think in the textbook they just do 273. If you want to be more precise, you can put the 0.15 there. But for the subject, just stick to 273. It's just going to make your life easier. And this then is 303 Kelvin. Right, so not degrees Kelvin, just Kelvin. Degrees Kelvin does not exist. All right, so I will take a look at a few examples on how to do the calculations here in a second. So where we can use a thermistor is in something like a water heater or a geyser. So remember also with a circuit diagram, your circuit components in your diagram doesn't necessarily, how can I put this? So basically, you're going to have your heater element and your thermistor here. They're going to be in the same environment, right? So you want to measure the temperature of the water in a tank or essentially a geyser. But because the heater element is on AC power, we're going to need a relay to switch the heater element on and off. Now, essentially what's going to happen here is, so we just have a simple voltage divider circuit here. So your relay coil, this has a resistance associated with it. And then you also have a rheostat here, which is an adjustable resistance. Now, essentially what we're going to do here is we want this heater element, or rather we want the water to be, let's say, at a certain temperature. Then you're going to adjust the rheostat basically to where you want it. Now, a relay coil, so what you guys need to keep in mind here, a relay coil needs a specific voltage. Not really specific. It needs a minimum voltage for it to be activated. So you might have something like a 12-volt relay, um, or rather say, let's say the coil of a relay needs 12 volts, right? So this coil might be triggered at, let's maybe say at 10 volts, right? So that will be the minimum voltage that you need for that coil to be switched on. Any voltage lower than 10 volts is not gonna be, it's not gonna cause a strong enough current to flow through that coil to have it triggered. Right, so that's also very important to keep in mind here. So that's essentially what that rheostat does. You're basically adjusting the amount of voltage that will be present across the relay coil as well. So essentially what's going to happen is if we're under cold conditions, the voltage here across the relay coil is big enough to switch the, in fact, no, I'm having this the wrong way around. So when this heater element is, yeah, so at start, so let's say the water is cold, then the relay, as you guys can see here, is set to the normally closed contact. So the heater element is on. So it's going to start heating up the water. Now, as the water is heated up, the voltage across your rheostat, so not the rheostat, the thermistor. So remember the thermistor's resistance is going to go down as the temperature increases. So the thermistor's resistance is going to go down, which means the voltage across it is also going to go down, which means the voltage across the rheostat and the relay coil is going to go up. So the voltage here is going to go up and the voltage here is going to go up. Up until, yeah, so this is where the rheostat comes in. So the rheostat, by adjusting it, that's going to determine when the relay coil will have a high enough voltage. Right, so when you reach a certain resistance here with your thermistor, that's then going to also be associated with a certain voltage across your relay coil, which is then going to switch your heater element off. Right, and then the water is going to start cooling down. When the water starts cooling down, I don't know why I have a full here. Now, okay, cool. Switch it on by accident. Okay, so with the resistance, yeah, so with the water cooling down, the resistance of the thermistor is going to go up, meaning the voltage across it is also going to go up, meaning the voltage across the other two is now going to go down. And then you're going to reach again the latching voltage of the relay, or going to go below the latching voltage. And then the relay is then going to switch back to the normally closed position, switching the heater element on again. So it's sort of going to maintain an average temperature over time. Okay, so that's essentially how this circuit works. Yeah, so before we go into inductive transducers, I am going to just continue with, I'm just going to do an example here for the thermistor, maybe two examples. So let's quickly take a look here. There are, however, other transducers in this chapter that I do not have in the slides that you guys should go and look at as well. For instance, I don't have infrared and fiber optics in the slide, so you guys should go read through that. Also, what I don't have is a Hall effect sensor. Guys should also go read through that. Okay, I'm just going to get 8.2.5 here as well. We can do this one as well. Okay, but let's take a look at 8.2.3. It's a pretty straightforward calculation here. Okay, so we're told the value of a thermistor is 5 kilo ohms at 25 degrees C with a constant B of 3,500. Right, so for 8.2.3.1 there, they ask us what the values of these resistors need to be for, yeah, so we can consider this now 25 degrees C, almost room temperature. So we can essentially just pick those resistors at the same size. So we can say R1 equals R2 equals R3 equals RT. Actually, you can actually say RT at 25 degrees C, which is then equal to 5 kilo ohms. Right, so that one was pretty easy, done. You can, however, you can pick different values. So for instance, that will still give you balanced voltage. So you can, for instance, maybe pick R2 as 5 kilo ohms and R1 as 1 kilo ohms. But then if you pick R1 as 1 kilo ohms, then R3 also needs to be 1 kilo ohms. Right, so that will just keep the voltage division between points A and B the same. But we're not going to take that route though. Okay, so then for 8.2.3.2, they ask us to calculate the gain of the amplifier here at 30 degrees C in order to produce a reading of 15 volts on the voltmeter. Right, so this is actually quite a tricky one, because you guys need to know that you actually have to know what the difference between the voltages are between those 2 points. Right, so the first step here would be for us to go and calculate what our thermistor resistance will be at 30 degrees C. That will help us greatly. But as you guys notice, we do not have the constant A. We don't know what that is. We need to go find out what that is. So that would be our first thing that we need to do here. Right, so we know what our resistance is at 25 degrees C. So that's basically going to be 5 kilo ohms, then equal to constant A multiplied by e to the power of I think it was, just quickly check. B over T. Okay. All right. So the temperature in this case, that's going to be 25 plus 273, which is 298 Kelvin. Is then A e to the power of 3,500 over 298. If I can stop switching my numbers around. And then at 30 degrees C, okay, so we actually have enough information there to calculate A. And so it's going to be 5,000 divided by e to the power of 3,500 over 98. Give me a few seconds to calculate this. That is e to the power of 3,500 divided by 298. And that should give you an A value here of, so if we round it, 0.04. Okay, so we can work with that. And then the next step would be to calculate what RT is at 30 degrees C. And that's then going to be 0.04. So A multiplied by e to the power of, so now we need to go and calculate our new temperature here of 30 degrees C, or our new Kelvin temperature. That is then 3,500 divided by 303, 0.04 multiplied by e to the power of 3,500 divided by 303. And that should give you 4.156 kilo ohms of resistance. That's not our final answer yet. We need to go. We actually need to. I would say the easiest thing now to do is to go and calculate what the voltage drop is between point B and that point there. So we want to go calculate what that is. That is not VAB, by the way. VAB is between points A and B there. So we have a source voltage here of 10 volts. Just pick a different color here. So I'm just going to squeeze it in here. So yeah, so the voltage B there, so VB. That's then, yeah, so we can use the voltage division formula here. So that's going to be our 10 volts multiplied by RT over RT plus R3. So that's now this 10 multiplied by this 4.156 kilo ohms divided by, which is now essentially going to be 9.156 kilo ohms. So I'm not writing the kilo ohms here because it's going to cancel out all the times 10 to the 3. So that's 4.156. 4.156 divided by 9.156. So that's going to give you 4.5, yeah, so 4.539 volts we're going to have there. Right, but we also need to go actually and calculate what the voltage across at point A is going to be. Voltage at point A is going to be quite easy to calculate because R1 and R2 are the same values. So when these two are equal, that just means that the source voltage is just going to split equally between those two resistors. That means VA is just going to be VS over 2, which is then 5 volts. Not always the case. If those resistors were different values, you would have had to use the voltage division rule there. And that means that VAB, so the difference between these two, that's then going to be 5 volts minus the 4.539. And that's going to give you 461, bugger off, 461 millivolts. Okay, so we need to change that to 15. That's, yeah, so basically we need to change that difference now to a 15 volt output. So we basically have that voltage sitting here between the terminals there of our amplifier, but we want a 15 volt output. Right, so gain, that's basically V out over V in. And we want to know what the gain of the amplifier needs to be. So that, okay, so our output voltage, that's 15 volts. Our input voltage, that's going to be 461 millivolts or 0.461 volts. And we need a gain of 32.538. Right, and gain is going to be unitless. Right. Cool. Any questions up until this point? So you guys can see, you guys shouldn't be intimidated by Whetstone bridges. They're actually really easy to work with. All right, so yeah, so that actually gives us a very, yeah, there's actually a reason why we use Whetstone bridges and not just a voltage divider circuit. Reason being is that the relationship, yeah, so if we were to do this, resistance is equal to voltage over current. So if we were to plot the resistance as our y-axis component, and well, either the voltage, actually, if we plot the current then as our x-axis component, you guys can see there's not a a linear relationship. I'm just trying to remember here, but yeah, there's a problem. You end up with a non-linear relationship with one of the quantities that you want to measure. And yeah, so basically what the Whetstone bridge does, it linearizes that non-linear relationship. Okay. Right. Okay, so that was 8.2.3. So let's take a look at 8.2.5. It's a little bit more of a tricky question. I think let me maybe move out here a little bit just so that we have space. Right. So yeah, so this question is actually a question that does crop up very often in the exams, where we have a thermistor that has a value of 20 kilo ohms at 10 degrees C, and then a value of 10 ohms or 10 kilo ohms at 30 degrees C. So we have two different operating conditions. The first part of the question, we need to go calculate what our constants A and B are going to be. So we don't know. So we need to go find that. We're given very minimal information on this, but we're at least given two operating conditions. And we need to go calculate what the resistor value is going to be at 30 degrees C. This is kind of dumb because that's already given to us. So I'm going to change that value. So let's maybe change it to something like, yeah, so let's pick something between 10 and 30, something that we wouldn't know. So let's think here. Maybe pick 20, 25. So we've been working with 25 a lot, so let's just keep to that. Right, so let's do 8.2.5.1. So essentially, you are going to solve this by doing simultaneous equations. So if we take the temperature, so for a start, the 10 degrees C, so that's going to be 10 plus 273. It's going to give you 283 Kelvin. And then for the 30 degrees C, T plus 273, so we already know that's going to be 303 Kelvin. Right, and then you're going to write down the formulas for these. So this is essentially your thermistor resistance. So you have your 20 kilo ohms, then equal to A multiplied by e to the power of B over your temperature. So that's 283. And on this side, you're going to have 10,000 is then equal to A times e to the power of B over, that's 303. Okay, so what you can do is you can either, so you guys can see that this side here is essentially 2 times that side there. So you can do that as well, and then just equate the two to one another. Or the easiest way to do this is basically to divide one into to another. That's another way of doing it. But I think let's go with equating them with one another. So what you're going to have here is basically A. So if we do that, you're going to have A e to the power of B over 283 is then equal to 2 times A to the power of B over 303. So those two will be equal. As you guys can see, the nice thing that can happen here now is that these A constants will cancel out, and we end up with e to the power of b over 283 is then equal to 2 e to the power of b over 303. Actually not a train smash. In fact, you can then do this. 2 is equal to, or we can just put the e's on the left rather. So that's going to be, yeah, so if you divide the one e into another, so that's basically going to be b over 283 minus b over 303 equal to 2. If you take the natural logarithm, so ln on this side, to get rid of the e, that becomes b over 283 minus b over 303 is then equal to ln of 2. Ln of 2, just see what that will give us. And that's going to give us a nice 0.693. The other way you could have done, yeah, there's another way that you could have done this. You could have actually just divided this equation into that one. Can also work. But then you can essentially just end up with the same that we had here. Anyways, so now we can actually go and do some calculations here. Right, so this is where things are a tad bit tricky, but it's not that bad. So you can end up with b, can take it out as a common factor there. 1 over 283 minus 1 over 303 is then equal to 0.693. 0.693 divided by 1 over 283 minus 1 over 303. It's going to give you quite a big value there. That's 0.693 divided by not 1.1 divided by 283 minus 1 divided by 303. And that should give you 2,971.203. So there's your B constant. A constant. So essentially now what you can do is you can back substitute into one of your equations, any one. I'm just going to use the 10,000 one. It's probably going to be the easiest. That's it. Essentially then going to be 10,000 is then equal to A times E, and that's going to be 2971.203 divided by our temperature there of 303 Kelvin. And then A is going to be 1,000 or 10,000, sorry, 10,000 divided by e to the power of 2971.203 over 303. 2971.203 divided by 303. So that should give you 0.551. Okay, so we have our two constants done. Now the second part of our question here, we need to go calculate the resistor value or resistance of the thermistor at 25 degrees C. So now that we have our constants, we can actually do that quite easily. So for a start, the temperature in Kelvin, that's going to be 25 plus 273, which is going to be 298 Kelvin. And the resistance at 25 degrees C. That's going to be, okay, so we know where our A constant is. Know what our B constant is, which is 2971.203, about temperature of 298. And that will give you a resistance of 11.784 kilo ohms. Right, everyone happy? Everyone good? Any questions? Okay. Yeah, so we don't have a ton of time left, so I'm gonna fly through a little bit through some of the other transducers here. Okay, so the next one that we have here is inductive transducers. So essentially, inductive transducers, like we've discussed, I think last week, they're gonna be dependent on changes in magnetic field characteristics. So, for instance, if you have a coil here and you have a piece of iron moving into or closer or into the coil, that's going to change its inductance, and thus that's also going to change its so the voltage and current. Yeah, so either going to change the current through it or going to change the voltage across it. Right. This is especially useful in AC systems where you have where you can actually see the change in reactance. Now, actually, one of the more common applications of an inductive transducer would be the linear variable differential transformer, or LVDT. So essentially what you have here is you have basically a primary winding that's excited using an AC waveform. And you have an iron core that displaces into, well, can displace either in one or two directions. And then your output here is then generated by two secondary coils. And also take note that the secondary windings are counterpolar to one another, connected in series, right? So if the iron core moves one side, then you're going to have a voltage, let's say, generated as such, and a voltage there. But you guys will see that the negative is then connected to the negative, and yeah, the positives will then give you your output. Now, the cool thing with linear variable, or LVDTs rather, is that you can actually detect direction as well. So this is a very good form of displacement measurement, especially if your displacements are not too far. So just to give you guys an example where LVDTs are used. So LVDTs are used, for instance, in aircraft landing gear. So basically, you can actually see whether your landing gear is either extended or retracted. So for the pilot, that's a very important information, especially if said pilot is coming in for a landing. Just trying to think here of other places. So yeah, so anywhere where you would have some form of extension and retraction, LVDTs can be used there. Especially if you need to know the direction of motion, and if you need to know whether something is extended to its maximum or retracted to its maximum. Um, so so that makes LVDTs quite valuable in such applications. So one application that we do have here is the use of a motor to drive something. This can actually be a setup that can be used in the landing gear of an aircraft. So effectively what we're doing here is, so it's an LVDT being used in a closed loop application. And so we're making use of two LVDTs. We have a reference LVDT and we have a feedback LVDT. So here's your feedback one. And you guys can see the feedback is not necessarily electronic. It can be mechanical. So in this case, we have a mechanical feedback that's then converted to an electrical signal by the LVDT. All right, so your reference LVDT, that thing is going to be adjusted. So you have a displacement input here. So that's your reference. And yeah, so that's going to generate a voltage, and then you're going to have your second or your feedback LVDT here. So essentially, if these two's, so if their cores, if their cores are in the same position, then the difference in voltage here is going to be 0 at the servo amplifier, and that's obviously they're not going to send. You cannot amplify 0, so the motor is not going to be driven. And yeah, and that's pretty much it. So that indicator, that can be replaced with something like aircraft landing gear or an arm or something that or lever that you want moved. Um, but in any case, so let's say for instance let's say we have an airplane, and let's say the landing gear is fully extended. So we then move our core in this direction. So essentially what now is going to happen is now our cores for the two LVDTs are going to be in different positions, which is then going to generate a difference of voltage here at the servo amplifier's input, which is then going to amplify that difference in voltage. That's going to be sent onto your motor's driver circuit. The motor is going to start rotating, and like I said here, the motor is also going to be mechanically linked to the feedback LVDT, which is then going to adjust its core also to the same position, or well, it's going to adjust the core until it is at the same position as the reference LVDTs, and then then the process is going to stop. Right. So yeah, so that's the use of LVDTs in closed loop control applications. Tacho generator, also an inductive transducer. So essentially, so essentially it's a two-phase induction motor that you mount onto the shaft of a machine in order to measure the speed. In fact, so here you have an AC applied signal. I believe it's an AC. I can't remember if it's AC or DC, but in any case, you have a voltage applied to this coil here. In fact, I think it's a DC. Yeah, so you have a voltage applied here that induces current into the conductors here. So essentially, the Tacho generator is almost like it is a generator of sorts. So you induce a current here, and then so basically that current is now going to have you're going to have a magnetic field around your armature conductors, and that magnetic field is also going to collapse. And so you're basically going to then induce a voltage across this coil, which we can then measure. And so the speed at which your machine is rotating is then proportional to the voltage that you read out here. Right, so there is a closed loop system making use of a Tacho generator for speed control. So again, there's our reference voltage. So this is especially, so this, in this case, this would be for something like a DC motor. So there again, you have a comparator, you have your Tacho generator. So if your Tacho generator, so it's going to give you your feedback voltage. So the feedback voltage and the reference voltages are the same. That means you're running at the speed that you want to run. Then the comparator output is going to be 0. But let's say we adjust, so we want the machine to go faster maybe. So we're going to increase the voltage here. In fact, if we go that way, we're decreasing the voltage. So we want to increase the voltage. We want to measure the whole voltage across RV, for instance. Then you're going to get a difference in voltage here. That's going to go to your motor control circuit. And so what you guys will see, so the feedback is going to be different. So that motor control circuit is now going to get the error signal. It's going to speed up the motor. And that means the tacho generator's voltage is now going to change because now the motor is speeding up. So the tacho generator's voltage is going to increase up until where it's equal to the reference voltage again. Then your motor is going to then run again at a constant speed. Then you also have synchro systems. So it's essentially uh, almost looks like a three-phase star-connected system. Essentially what you have is you have yeah, so with synchro systems, you're always going to have a transmitter and a receiver. So you essentially have three coils. So on the transmitter side, you apply then an AC signal to your rotating coil. So this coil actually rotates. So physically, yeah, so physically this coil rotates around in your transmitter. And depending on its orientation, that's now going to induce voltages in these coils, so different voltages, right? So the voltages are not going to be equal for each of these coils. And yeah, so if that doesn't match with the voltage, yeah, so basically what you then get, okay, so basically what you then get is the voltages are then going to be, you're going to have currents induced in those coils and voltages over them. And yeah, so now if let's say the position of this coil and yeah, so if the position of your two rotating coils are the same, then your amplifier is not going to have anything to amplify. But let's say we adjust our transmitter, so that the transmitter is going to be your input side. So if we adjust this one, so we rotate it a little bit so that we can point our turret in a different direction, then this is then going to cause a difference in voltage across this coil, the moving coil here. And that's then going to go through the amplifier. Amplifier is then going to drive a motor circuit. That motor circuit is then going to, through a mechanical linkage and gearbox, rotate your turret. Turret is going to rotate. Turret is mechanically linked to the receiver of your synchro system, and then it's going to rotate until the two moving coils are matched again. Right, so that's essentially what's going to happen here. And then the nice thing here is you can actually kind of measure the direction here as well. So if the voltage difference is, let's say, negative, then the thing, for argument's sake, will have to rotate counterclockwise. If the voltage was positive, it would have to rotate clockwise. So yeah, so you guys can see there's another example on that. Yeah, so I see we are pretty much out of time. So guys, there's also photosensitive transducers. Yeah, so you guys should also go take a look at these circuits. So some of them, yeah, so just go try and figure out which ones. I think the textbook does explain which ones will turn the relay coil on or off. So yeah, so you can essentially do the same thing with LDRs, photodiodes, light dependent transistors or phototransistors. And yeah, in actual fact, they don't really look like that. Phototransistors are essentially just something like this with the base exposed to uh, light. So that's the actual way it actually operates. But I mean, but I've seen, but this layout, yeah, this component also exists, but it's not really, kind of defeats the purpose here, having a base connection. But you do get this, but not used often. This configuration of the phototransistor is actually used more. And then you have light activated SCRs. So now on top of having a gate signal, now you also need to have incoming light as well. Yeah, so you can also use them to do things like AND and OR gates. So yeah, but you guys will see in the textbook there's also a whole section on infrared and a section on fiber optics. I would urge you guys to go read through that. Not a lot of questions, or rather, let me put it this way. It's not very common for the exam, or very common in the exams that questions do come from those two sections, but I have seen lately, especially from the infrared section, there has been a few questions in the exams coming from there. But any case, guys, if you don't have any questions, have a good evening, and good luck with the exams. Good luck with your second test. And yeah, and hopefully if I see you guys again, it would be for N6. Right. Cheers.